So now we extend our study to a particle which is moving in a plane rather than along a straight line. Okay, plane means we are now talking about motion in 2 dimensions, motion in 2D. One example of motion in a plane or a 2 dimension could be, let's say, an insect which is crawling on the floor, an ant which is crawling, going anywhere on the floor. So it has essentially a plane to walk upon, and it can take turns to move wherever it wants. It can move in a curve also, like this, wherever it wants, right? So such a motion will have now 2 coordinates in terms of which we have to study the motion of the particle. For example, if we take one direction as along the x-axis and the other direction which we are taking perpendicular, understand that I've drawn a plane, a floor like this. So the x and the y-axis are actually perpendicular to each other. So it is in terms of these 2 variables now that we shall try to study the motion of a particle. So motion in a plane is studied in 2 variables. Generally, we take those 2 variables as the x and the y coordinates of the particle, and we in that case we say that we are assuming that the particle is moving in the xy plane, right? You can always attach a Cartesian system or xy axis system with a plane, right? We can always do that, and that makes our study of the motion easy. Okay, so to understand this in detail, let us take up the xy plane like this, the general way in which we take it. This is, let's say, the x-axis, the horizontal axis, this is the y-axis, and let's say there is a particle which is undergoing some random motion, and let's say we try to study this particle when it moves from, let's say, a position P to another position Q over here. How do we do that? Let us consider the initial position vector of the particle, which is the position vector of the point P. Let's call it vector R1. And the final position vector of the particle, let us call it R2, which is the position vector of the point Q. Starting from the origin, these are vectors OP and vector OQ. So these are the 2 position vectors corresponding to the initial position and the final position. For this particle then, do you all understand that the displacement vector will be given by the vector that joins the initial position with the final position, which will be this vector. The vector PQ is the displacement vector, isn't it? And for this displacement vector, see that using the triangular law of vector addition, we can write the vector PQ, which is also our displacement vector S, as the vector R2 minus the vector R1. See this carefully. The vector R2 in this particular figure is the sum of R1 and S, this vector we are calling as S now. So in this case then we can write vector S as R2 minus R1. Sometimes you can also write it as the vector delta R, the displacement vector. That gives us the difference between the 2 position vectors, the initial position vector and the final position vector. Okay. Now, if we consider the x component of this vector x, vector S, and the y component of the vector S, both of these will be given by these 2 horizontal and vertical lines that I have drawn here. If we call the length, let's call this point, let's say, as the point S, let us take it as R. Then if I consider the length PR as some x and the length QR as some y, see that the vector S then can be written as x I cap plus y j cap. What we have done here, we have split the vector x into its 2 components. The horizontal components, which will be x in magnitude and pointing along the x direction, where we have a unit vector I cap, and the other vertical vector y, which is pointing along the y axis, having a unit vector j cap, right? So this is how we can write our vector S as in its component form. Writing a vector in a component form we have already learned in the chapter vectors. So this is the displacement vector of the particle in terms of its x and y displacements, right? Now we can go a step further and we can try and find out the velocity of this particle at any point in time, v. If we talk about this particular displacement, which we have taken to be a large displacement, a substantial displacement, we can talk about average velocity, which by definition will be the total displacement by the total time, right? So if we know the time that the particle has taken to move from P to Q, we can simply say that it will be x by t I cap plus y by t j cap. X by t will give us the rate at which the x displacement is covered, so we can call it the average velocity along the x-axis, and y by t will give us the rate at which the y displacement is covered, so we can call it as Vy, the average velocity along the y direction, into j cap. But as we have discussed in the previous videos, we know that this way of defining velocity is not a very refined way. Generally, we are looking forward to find out the instantaneous value of velocity of a body, isn't it? And to find out the instantaneous velocity, so what we have got here is the average velocity, Va, Vg. But if we look for the instantaneous velocity, we need to take this time interval t down to a very, very small interval. And in that case, the basic definition that we get for instantaneous velocity is ds by dt. When we find out the rate of change of displacement for a very small interval of time, dt, the corresponding displacement is ds. So when we use this particular operator on this expression, we will get on the right hand side dx by dt I cap plus dy by dt j cap, which is a more accurate value for the velocity of the particle at any instant of time. And see that this term dx by dt, which is the instantaneous rate of change of the x displacement, gives us the instantaneous velocity along the x-axis Vx, plus dy by dt will give us Vy, the instantaneous velocity along the y-axis, and this is a more accurate expression in comparison to this one. So these values of Vx and Vy that we get here will actually be average values. Let us mention that here. So these are slightly different from what we have obtained here. This is a more accurate expression in terms of the instantaneous value of velocity. Okay. So knowing the displacement of the particle and knowing how its x and y directional displacements are changing with respect to time, we can find out both the components of velocity of the particle. You can observe one thing here, that the velocity along the x-axis has only to do with the x directional displacement. It has no relation with the y directional displacement. So in that sense, the velocities along the x and the y direction depend upon the x and the y directional motions respectively. They do not depend the other way around. So in a way, we can say that the x and the y directional motions are kind of independent of each other. The x directional motion depends on only x directional quantities, and the y directional motion depends only on y directional quantities. We shall look at this aspect a little more in detail when we study the projectile motion, which will be the next video, the next topic to be covered. Now we move on to finding out the acceleration. Once again, since we would be looking for the more accurate value of acceleration also, we shall directly find out the instantaneous value of acceleration now, which by definition is the rate of change of velocity, dv by dt. And we have already got v with us, so we can use that here. So when we use this operation, the differential operation on v, we will get on the right hand side dvx by dt. As we know, the value of v is given by these two terms, into I cap, plus dvy by dt into j cap. See once again that the rate of change of velocity along the x-axis with respect to time should be nothing but the acceleration along the x-axis, isn't it? And dy by dt should be the acceleration along the y-axis. So that is how we get the acceleration. We can differentiate the x direction velocity and the y direction velocity separately to get the x directional acceleration and the y directional acceleration. So this, once again, this is telling you the same thing, that the x directional motion and the y directional motion, they do not depend on each other in any way. They are independent of each other. Okay. In fact, once we understand this, we can go further and say that in case if the acceleration of the particle along the x-axis is a constant, that means it does not change, then we can go back to our study of uniformly accelerated motion, knowing that when the motion is uniformly accelerated, the equations of motion are valid. We can say that if only the motion along the x-axis has a constant acceleration, we can use the three equations of motion: v is equal to u plus at, s is equal to ut plus half at squared, as well as v squared minus u squared is equal to 2as. We can still use them, but now only along the x direction, because it is only the x directional acceleration which is constant. So what you do is you make slight changes in this equation. You subscript everything, all the vector quantities with x, thereby understanding that we are using these equations of motion only along the x-axis. For y directional motion, we can't say for now. The only thing that we know is the acceleration along the x direction is constant, so we are using the equations of motion along the x direction. See that all the quantities used in these equations, all the vector quantities, have to be taken along the x-axis. The components of velocities along the x direction have to be used here in these equations. Okay. This is a very important understanding because we use this to study many other motions. In fact, the next topic, projectile motion, is solely based upon this aspect, that the motions along the x and the y direction are independent of each other. Similarly, if ay is a constant, then we can use similar three equations along the y-axis also. So you will have vy is equal to uy plus at as the first equation of motion, sy is equal to uyt plus half ayt squared, and vy squared minus uy squared is equal to 2 ay into displacement along the y direction, that's sy. Okay. So now, just to understand this in more detail, let us take up an example. So it is given to us that there is a particle which is moving in the xy plane. This is the x-axis, this is the y-axis, and it is given that the particle is moving in such a way so that its acceleration is 2 meter per second squared, such that it makes an angle of 60 degrees north of east. This is the direction of acceleration, 60 degrees north of east. Do we understand what this acceleration is? This acceleration will look like this. Acceleration vector is 2 meter per second squared and making an angle of 60 degrees towards north of east. Understand that this is the eastward direction, so making an angle of 60 degrees towards north here means this angle should be 60, right? So this angle here is 60 degrees. This is what we are talking about as the acceleration. What else is given? It is also given that at t is equal to 0, when we start observing the particle, the initial velocity of the particle was found to be 10 meters per second along the x direction. So 10 I cap, this is the vector u. So let us show that also in the same figure. This is the direction of the initial velocity vector along the x-axis. U is equal to 10 I cap. Okay. Now the question is to find out the velocity of the particle and its displacement at t is equal to 5 seconds. This is the question in hand. So see, do we understand that the acceleration of this particle is a constant? Since it is given to be a constant, the only thing is it is in a plane now, it's not along one single direction. The acceleration lies in the xy plane. So what we can do is, We can first find out the components of this acceleration along the x and the y direction, and then study the x and the y directional motions separately, right? So how do we do this? First thing is, we can say that the acceleration along the x axis. Now for that you need to once again have an understanding of component of vectors. What will be the x directional component of acceleration? Ax. Understand from this figure, it will be a cos 60, right, which in this case will be 2 times cos 60 is 1 by 2, so 1 meter per second squared. This is the value of Ax. What is Ay? Ay, from the same understanding of component of vectors, will be this vector over here, which will be Ay, and magnitude wise it will be A sin 60, which in this case will be 2 into sin 60 is root 3 by 2. So this becomes root 3 meters per second squared. So we get the accelerations along the x and the y direction. Now let's write the initial velocity also. It is given that the initial velocity is all along the x axis, so ux is 10 meter per second, whereas uy is 0. There is no initial velocity along the y direction, right? And now what we can do is, we can use the equations of motion along the x axis and y axis separately. So to find out the velocity at t is equal to 5 seconds, we can use the first equation of motion. First along the x axis, v is equal to Vx is equal to ux plus Ax into t, and substitute the values. Ux is 10 plus Ax is 1 into the time in which we are trying to find it out is 5 seconds. Solve it to get Vx is equal to 15 meters per second. This is the value of Vx. Similarly, can we say that Vy, which will be uy plus ay into t, should be uy is 0 plus root 3 times 5. So Vy will be 5 root 3 meters per second. We can just keep it like this. Now we have got the two components of velocity. How do we get the net velocity vector then? Do we know that we can combine the two vector components like this and write vector v as vxi cap plus vyj cap, where we also know that if we want to find out the magnitude of this velocity vector, all we need to do is do square root of vx squared plus vy squared. This comes from our knowledge of vectors. So we understand that vector v will be 15 I cap plus 5 root 3 j cap, right? And also the magnitude of vector v will be square root of 15 squared plus 5 root 3 whole squared, which you can solve now and get your final answer. Here we see that we can take 5 root 3 common out of the whole expression, and inside we will have root 3 squared plus 1 squared, that will be 3 plus 1 root of 4, which is a 2. So 2 will come out and we will have 10 root 3 as our final answer for magnitude of velocity. This is how we get the magnitude of velocity. So we have got our velocity in two forms. One, we have got the complete vector v, the other we have got the magnitude of v. If we want, we can also find out the angle that the velocity vector makes with the x or the y axis. Do you understand? From here we understand that vx is 15, vy is 5 root 3. So velocity vector v will be a vector that looks like this, whose x component is 15 units, 15 meters per second, and y component is 5 root 3 meter per second. So if the velocity vector makes an angle phi, let us say, with the horizontal direction, then we can easily write tan of phi is equal to the opposite by the base. Tan of an angle is the opposite by the base of the right angle triangle. So that in this case will be 5 root 3 by 15, which will be 1 by root 3, and you know that this gives us the value of phi as 30 degrees. Tan 30 is 1 by root 3, isn't it? So we can actually get the angle that the velocity vector makes with the x-axis at this particular time when the information is being asked, right? So we can get all the information about the velocity. Now for the second part of the question, this was the first part, finding out the displacement vector s, b part. Again we can use the equations of motion, this time the displacement equation. Sx is equal to uxt plus half at axt squared, the second equation of motion along the x direction, and the second equation of motion along the y direction. Let's substitute the values. Ux is 10, t is 5 plus half, acceleration along the x direction was 1. So 1 into here we will have a 5 squared, right? So you can solve this to get 50 plus 25 by 2, which when you solve after taking the LCM, we will get 125 by 2 meters as your displacement along the x-axis, right? Displacement along the x-axis, by the way, can be written as the x displacement, just like x also. Similarly, Sy will be uyt, which is 0 because uy is 0, plus half ay is root 3, t squared means 5 squared, 25. So you have 25 root 3 divided by 2 meters as the y directional displacement. Sy, you can also call it simply y. Okay. So what do we understand from here is that in the time of 5 seconds, the particle travels this much distance along the x-axis and this much distance along the y-axis. So if you want to write the net displacement vector s, it will be sxi cap plus syj cap. If you want to find out the magnitude vector s, it will be square root of sx squared plus sy squared, right? The mathematics can be done now. So understand that in this case, if we assume that let's say the particle was at the origin initially, let's say the particle was over here at the origin 0, 0 point initially, and it moves to the new position in 5 seconds, which is somewhere here, we can consider the coordinates of this point as x, y, the ones that we have just now found here. This x and this y, these are nothing but the coordinates of the final position of the particle after a time of 5 seconds.